Okay, so let's start with the session. So, hello everyone, a very warm welcome and good afternoon, good morning, or good evening to all of you from different parts of the world. So, dear authors, distinguished session chairs, esteemed guests, welcome to the technical session 9C. I am Yashita and I'll be your moderator for this session. So, on behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you all to the 10th World Conference on Information Communication Systems, Software Security and Sustainability, which is WorldS4 2026. So, this landmark 10th edition of the conference is being conducted in a hybrid mode, while the physical conference took place yesterday in London. We are delighted to connect with you all virtually through Zoom on 29th and 30th of July. And we have an exciting lineup ahead. I'm sure that we'll have some insightful discussions and innovative ideas. So, a few quick session guidelines before we start. So we will be having a total of six presentations scheduled, and each presenter will be given 10 minutes for their presentation, followed by 2 minutes for question and answers. And at the ninth minute mark, I will give a gentle reminder so everyone can wrap up comfortably. Also, we kindly request everyone to stay with us until the closing remarks. Additionally, if you have any questions, technical issues, or updates during the session, please feel free to put them in the chat box. Me and my co host will be assisting you. And before we begin, it is my honor to introduce you all to the session chair for today. So, first we have Dr. Preeti Parvekar. She is a professor in Department of Computer Science, Engineering at Geetham University, Hyderabad. She has been an academician from last 23 plus years. She is a member of IEEE, ACM, and CSI. Her research interests include IoT, cloud computing, machine learning, wireless sensor networks, software engineering, information retrieval systems, social media, and data mining. So, welcome to the session, Preeti ma'am. Would you like to say something to start the session?
Yeah, thank you, Yashika. Thank you for the nice introduction. And I wish all the best to all the researchers who are here. And we are looking forward to listen to your innovative research. Thank you.
Thank you so much, ma'am. So, our second session chair, our Dr. Kanakarna Fanifong, who is an associate professor in business administration at Rajamangala University of Technology, uh, Tawan, uh, Tawanok, Thailand, with over 21 years of experience spanning academic administration, industry, academia collaboration, and lecturing. His core research interests encompass information technology management, enterprise architecture, business resilience, and educational technology. So he will be joining us in a bit. He's not joined yet, so we will proceed with the lineup for today. So for our first presentation, we have Maria Nazarkevich. Maria, are you present in the session?
I will share the presentation. I'm Daniel Korotic.
Okay, sure. So Daniel is here to present his paper, titled as "A Method for Adaptive Control of a Smart Enterprise with Weak Signal Detection Based on Multimodal Data." Yes, you can start sharing your screen.
Okay,
Yeah.
give me a second. I need to share my screen. Uh, Sorry, 1 second.
Yes.
Do you see my screen?
Yes, it is visible. You can start. And a reminder for all the authors that I request everybody to please finish their presentations in the given time, as we are time bounded and have to finish all the presentations in the given time. So you have 9 to 10 minutes. You can start, Daniel.
Sorry, do you see my main
Notes.
screen with
Yes.
presentation or with
Your notes are also visible.
your notes? Okay. Sorry,
Yeah.
1 second. Okay. Now you should
Yes, it
see
is
only
visible.
the main.
Yes.
Okay. Okay. 1 second, I open my notes then, and we can start. Okay. Good afternoon. We can start. Modern enterprise operate in highly volatile environments. Markets, competitors, and technologies change faster than ever. Crises and opportunities rarely appear out of nowhere. They are preceded by weak, barely noticeable signs. Our work focuses on how to automatically detect these weak signals using multimodal enterprise data. Okay, the concept of weak and strong signals was introduced by Ansoff back in the 1970s, but the classical approach relies on the expert panels, slow, costly, and subjective. Today, enterprises generate massive volumes of heterogeneous data every day, reports, social media, sensors. This creates an opportunity to replace manual expert judgment with an automated quantitative method. Here is the overall architecture of our method. The system collects external and internal signals from the multiple sources. This is our multimodal data. From this, we compute a single internal indicator of impact of the enterprise. The current value is then compared to the forecasted one, and if the deviation exceeds an acceptable threshold, the system flags a weak signal and generates a recommendation for a management decision. The key advantage of our approach is multimodally itself. We don't rely on the single data type or purely on the expert opinion. By combining financial indicators, social media date, news, and internal reports into one integral indicator, we significantly increase sensitivity to early signs of change. At the same time, the method remains transparent and mathematically grounded, unlike black box approaches. The detection mechanism itself is simple and mathematically precise. We compute a time series of the actual indicator, build a forecast for the next period, and once that period arrives, we compare the forecasted and actual values. If the deviation exceeds a predefined threshold, this is registered as a weak signal, an early warning of possible problem or emerging opportunity. To validate the practical part of our method, we solved a profit forecasting problem based on the R&D spending, administration cost, and marketing expenditures. We compare four methods: linear regression, support vector machines, random forest, and a neural network. Quality was assessed using the R-squared coefficient of determination, along with the mean absolute and mean squared errors. Experiments were run in Python using TensorFlow with GPU acceleration. The results shows that all four models achieve strong forecasting performance. Linear regression performed best with an R-squared of 0.9973, closely followed by random forest at 0.9972. Simpler methods actually outperformed more complex ones in accuracy. Support vector machines gave the weakest result at 0.9816. The neural network also showed good accuracy through with slightly higher error. Notably, linear regression was also the fastest in computation time, making it, along with random forest, the best balance of accuracy and speed. To summarize, we developed an adaptive management method for smart enterprise based on weak signal detection through the integration of multimodal data. Our experiments confirm the practical effectiveness of this approach for forecasting key indicators. Going forward, we plan to expand the data sources and adapt the method for crisis and unstable environment conditions. Thank you for your attention. This is all from my side.
Okay, thank you, Daniel. Preeti ma'am, any questions from your side?
Yeah, it was a good work. I would like to know from where did you collect the data set?
We get data set from the internet. It was open data set, as I know, with 100 or 1000 data from the best companies in the world.
Yeah, I can add some explanation here. So in the paper, the dataset is loaded to train the evaluations models. It contains the enterprise's financial feature, R&D spendings, administration costs, and marketing expectations, which are used to predict the company profits. So the paper doesn't name a specific external source for the databases. More broadly, the method draws data from external and internal segments.
All right. And in future, you have mentioned that you need to broaden the data sources. So, what type of data sources you are looking for the future work?
Mm,
The last point, future work, broader the data sources, application in crisis conditions. Could you
Yeah,
elaborate?
so in the future, we plan to use broader data sources and apply the method to crisis conditions, but the presentation lists this is as a future work. So expanding beyond the current sources are more external and internal signals to make the early detection even stronger. But yes, it's interesting question to think.
All right. All the best for your research. Thank you.
Okay, thank you, Daniel, for presenting. You can stop sharing the screen.
yes, thank you.
Yes. So for our next presentation, we have Marlon Kulatunga to present his paper titled as an integrated Kubernetes security framework with context-driven policy orchestration and ICAP-based content inspection. So Marlon, are you present in the session?
Hey Ashita, yes, I'm present. Am I audible?
Yes, yes, you're audible.
Let me share my screen. And thank you, Ashita, and good morning, good afternoon, good evening, everyone, and thank you for having me. So I'm here to present our paper, an integrated Kubernetes security framework with context-driven policy orchestration and ICAP-based content inspection. So this is a joint work with SLIIT, which is my university, and my researchers, fellow researchers are also studying there. So first I'll cover the problem we set out to solve. So what's actually novel about our approach, how the four modules of the framework work together, and what our evaluation on it. So let's get into it. Uh, so we started from two structural graphs in how Kubernetes security is typically done today. So the first is that admission control tools rely on fixed static policy catalogs. They don't adjust to the operational context of a namespace. A production namespace gets policed exactly the same way as a developer sandbox. So previous research shows that this causes encryption and audit login controls to be systematically skipped. So even in repositories that are actively maintained, and they found something striking, which is across more than 2,000 open source Kubernetes manifests, there were 1,051 distinct misconfigurations. And teams only ever got around to fix 60% of them. The second gap sits at the content inspection layer. So ICAP-based scanning services governed by RFC 3507 are run completely outside the Kubernetes control plane. So that means scanning pod health and traffic routing decisions are made in total isolation from each other. So researchers identify content ingestion as a high severity threat that infrastructure level controls alone simply can't mitigate. So one gap is the policy layer and one gap at the content layer. So our framework built to close both at once. So what is actually new here? So there are three things. So first is a 7-indicator namespace classification algorithm. So instead of trusting one label, it combines 7 weighted signals and reaches 96.7% accuracy tiering namespace correctly. And even when labels are missing, or deliberately falsified. The second is a dual engine compliance translation pipeline. So we are taking a single internal representation of policy constraint and deterministically compile it into both Rego and OPA gatekeeper and CEL based cluster policy for Kaiwano. So around 4,500 test payloads, the two engines agree on enforcement decision of 99.2% of the time. So third, an adaptive multi-signal wellness scoring mechanism for our content inspection pods. So rather than watching CPU and memory like a standard autoscaler, our custom operator blends 6 telemetry dimensions and reweights the depending on what actually is degrading. So surfacing failures that conventional autoscaling would never catch. So these three pieces are the core contribution of this paper, and I'll walk you through the mechanics of each one. So moving on to the system architecture, the 4 Kubernetes native modules with strictly directional dependencies, no circular coupling anywhere. So deployment gating is the sole label writer. It iterates every workload promotion before it's persisted and rejects anything with missing out of range fields outright. And its labels feed the policy orchestration module, which classifies the namespace and writes the enforcement artifacts, the Rego and Kaiwano policies. The classification is then pushed by webhook onto two downstream modules, traffic management, which generates tier-specific ISTO routing, and the content inspection operator, which manages the life cycle of our ICAP scanning pods. And there's a feedback loop. The content inspection operator continuously reports wellness scores back to traffic management. So traffic gets reweighted away from any scanning endpoint that starts to degrade. This wall design follows Burns and colleagues' desired state reconciliation model. And critically, every module here is independently deployable. You can enrich the policy library without ever touching the enforcement engines. So let's zoom into the piece there, I think, which is most interesting. So how to classify a namespace when you can't fully trust the label. So this is implemented as a Kubernetes controller build on controller runtime. And on every reconciliation cycle, it computes a weighted confidence score across 7 independent signals. The explicit environment label still carries the most weight at 0.35, but it's not decisive on its own. So naming convention, resource quota profile, network policy dynasty, and role-based access control privilege scope, and namespace age and churn rate, and image registry province together make up the other 0.65. So what that means in practice is if someone mislabels or maliciously tamper with a namespace environmental track, 6 other structural signals can still output the single falsified label through weighted consoles. So the result is tested across 60 namespaces, spun in fully labeled, partially labeled, unlabeled, and adversely labeled conditions, which gives out 96.7% overall classification accuracy. So once the namespace is classified, it needs to be mapped to actual enforcement. Here's how it works. So we maintain one internal representation of policy constraint, typed field constraint, engine agnostic, and that gets complied deterministically into 2 outputs, Rego for OPA gatekeeper and CL-based cluster policy YAML for Kaiwano. We do this because as Cisdiana and colleagues showed, the 2 engines reason differently. So gatekeeper favors Rego-based logic, Kaiwano in YAML native, and neither one alone expresses every cross-resource constraint we need. So on top of that, we apply a graduated compliance mapping for tier. PCI governed production namespace get the intersection of CIS level 2 and PCI DSS version 4.0. Standard production gets CIS level 2 alone, staging gets level 1, and development gets minimal baseline. This graduated approach is exactly what fixes the uniform enforcement problem Verdet and colleagues flagged earlier. The classification also drives how traffic gets routed. The traffic management module generates a store virtual service and destination rule resources, turn top tier. Development environments are optimized for rapid failover, and production environment prioritize the deterministic routing with strict circuit breaking, grounded in empirical findings of Selgafo and colleagues on ISTO traffic policy. It also maintains a service registry keyed directly to the wellness scores coming from our content inspection operator. When a scanning endpoint's score drops below a failover threshold, traffic reverts toward healthy endpoints automatically. And now the piece I think the most practically important, how we monitor the health of the content scanning layer itself. The content inspection operator manages our CLAM AV scan inputs as a Kubernetes custom resource. On every reconciliation cycle, it puts 6 telemetry dimensions: readiness, latency, signature, freshness, error rate, resource utilization, and queue depth, and combines them into a signal wellness score. Here, the important part is the weight isn't static. So under normal conditions, readiness and latency dominate the score. Under degradation, the weight shifts, signature freshes, and error rate take priority. So under high load, queue depth gets weighted up. So how did we validate all this? So our 5-node K3 cluster, 4 vCPUs, 8 gigs of RAM per node, and Ubuntu 22.04 running continuously for 72 hours. We put 60 test namespaces through it across all 4 labeling conditions and ran 4,500 admission review payloads, exercised 7 distinct wellness scenarios, and drove a synthetic traffic generator at 2,400 requests per minute, all aggregated through Prometheus. So I want to spend a moment on one result that I think best justifies the whole design of this framework. So look at the state signature scenario. So readiness sits at 100, latency is near the best value, error rate is near its minimum. And if you were watching the pod through the conventional GPU memory here, you would call it completely healthy. So every resource signal says so. I want to upfront about where the work stops. So everything here was validated on K3 specifically. So cross-platform testing on EKS, GC, and AKS is the natural next step. So particularly given documented ISTO vulnerabilities that would need re-evaluating on managed platforms. So our wellness testing didn't include adversarial workloads on zero-day simulations, which we need to properly characterize evaluation resilience, and the indicator weights and wellness weights were fixed by designing in its study. So a formal sensitivity analysis is a priority for future work, and we haven't measured webhook latency overhead under sustained load, nor address supply chain security and the image build layer. That's explicitly out of scope here. So to close, this work shows that 2 problems are usually tackled in isolation: context-blind administration control and context inspection that's disconnected from the orchestration layer and can be solved together in one 4-module architecture without touching a single existing workload. So thank you so much, and I'm happy to take any questions.
Yeah, hi. Could you just clarify one thing? Like this work
Yes.
has been done for the resource management or the workload management, or with respect to the security aspect?
It's done based on security aspect.
All right. So could this take care of all the kinds of vulnerabilities for all the layers which comes in Kubernetes?
Not necessarily, as I mentioned previously as well. So adversarial workloads on zero-day simulations, we cannot do it because those are like for an example, these are not how do you explain it? Like they are not given out in the world at the moment. So existing threats, yes, actually, absolutely. And there's a customization layer where based on the given frameworks such as PCI DSS and HIPAA and such cases, we can customize it based on the need of a company and etc.
It's a very nice work. So wish you all the best.
Thank you so much. Have a great
Thank
day.
you.
Yeah, thank you so much for presenting.
Thank you, Ashmita.
So up next we have Roneva Gilbert Thatheni to present his paper titled as Citizen Participation in E-Government, Evaluating the Impact of Online Engagement Platforms and Their Effectiveness in Fostering Democratic Governance in South Africa. So Roneva, are you ready with the presentation? or any of his co-authors is there on behalf of him?
Yes, I'm ready.
Yes, so you can start sharing.
Okay. Just a minute. I'm sharing. Are you able to see my presentation?
No, actually, the files are visible. The presentation is not visible.
Are you able to see it now?
No. You have to select the presentation tab. The presentation must be open at the background. Try once again.
Are you able to see it now?
Yes, it is visible. You can start.
Okay. Are you able to see the notes?
No, no, no. It is perfect.
Okay. Thank you so much. My name is Ronewanta Teni from CSIR, South Africa. So today I'll be presenting a paper with the topic Citizen Participation in E-Government, evaluating the impact of online engagement platforms and their effectiveness in fostering democratic governance in South Africa. So I co-authored with my colleague, Tumiso Tulare, also from the CSIR. Firstly, we'll be looking at the overview of the paper. The first section, we'll be looking at the introduction. Then the second will be the methodology, where we'll be looking at the literature review and the prisma diagram. The next will be the literature review, where we'll be looking at what extent do online engagement platforms contribute to democratic governance in South Africa and what factors influence their effectiveness. And then next, we'll be looking at the results, where we'll look at the online engagement platforms currently in use in South Africa and the comparative insight from global case studies. Then we'll look at the recommendations and the conclusion. So e-participation is the use of information and communication technologies to engage citizens in government, policy decision-making, and public service design. So the online engagement platforms such as social media, government portals, and mobile applications are key tools for facilitating e-participation. These platforms enable real-time communication and broaden access to information and provide citizens with opportunities to influence decision-making. So our research question will be, to what extent do online engagement platforms contribute to democratic governance in South Africa? And what factors influence their effectiveness? So on the methodology, we used the scoping review, and we sampled the literature that was published between 2016 and 2025. The sources include Science Direct, IEEE Explore, Springerlink, Google Scholar, and also the Google search engine. Keywords are e-government, e-participation, digital engagement platforms, citizen participation, and democratic governance. So the results from the Prisma diagram are as shown on the left, and the final studies included were 13 on the literature. So the benefits of online engagement platforms in fostering democratic governance. The first one, we looked at the access to information, which provide easier access to government information and reduce participation barriers. Transparency and accountability, which enables public monitoring of government performance. Then two-way communication ensures that stronger interactions between government and citizens takes place. The broader participation ensures that participation reaches diverse and geographically dispersed population. Efficiency and cost saving. This reduces administrative costs compared to the traditional engagement methods. So the key challenges include digital divide, low digital literacy, limited institutional capacity, weak government responsiveness, and platform fragmentation. The results demonstrate that online engagement platforms have the potential to significantly enhance democratic governance by improving transparency, accountability, and citizen participation. However, their effectiveness in South Africa remains uneven and highly conditional, shaped by the infrastructural, institutional, and the socio-economic factors. So now we'll look at the online engagement platforms that are currently in use in South Africa. The first one, we have the GovChat, which is a South African largest civic tech startup platform. It functions as an official digital communication channel, bridging the gap between citizens, local municipalities, and national government departments. The GovChat integrates WhatsApp and Facebook, and it has connected over 10,000 public representatives and 30,000 public facilities. The next one, we'll look at the My Home Affairs online portal, which is an official secure e-portal launched by the South African Department of Home Affairs. It is designed to modernize public services and allow citizens to process identity, civic, and citizenship status online. The next one, we'll look at the Collab Citizen app, which is a mobile platform designed to improve and streamline municipal service delivery, and communication between local government and residents. It is used by various local municipalities across South Africa to provide an official digital channel for citizen engagement. Next one, we'll look at the SARS e-filing, which is the official secure online platform provided by the South African Revenue Service, SARS, to allow individuals, individual taxpayers, businesses, and tax practitioners to manage their tax obligations digitally. So the SARS by 2025 had 10.2 million users, and it conducted 5.8 million auto assessments and refunded over 10.6 billion within 72 hours. So this shows how effective the platform is. Next, we'll look at the social media platforms such as WhatsApp, Facebook, TikTok, X, which is formerly Twitter, and YouTube. So these social media platforms serve as a critical channel for communication engagements, entertainment, business marketing, and citizen to government communications. Now, the comparative analysis reveals that South Africa occupies an emerging stage of digital participation characterized by growing platform adoption, but limited institutional integration and participatory depth. Across global cases, three critical
Runeva,
success factors
just a quick
emerge.
reminder that you will have to wrap up in next few seconds.
Okay, noted.
Yes.
The three success factors include integrated digital infrastructure, institutional responsiveness and capacity, and meaningful participation. So on meaningful participation, experience from Brazil highlights the importance of empowering citizens with decision-making authority rather than limiting engagements to consultation. So recommendations, the government should invest in digital infrastructure, expand broadband access, and improve digital literacy. The municipalities should increase citizen influence in decision and strengthen responsiveness to public inputs. On the platform design, we must ensure that ensure inclusivity and support people with disability, and also combine online and offline participation. In conclusion, the main findings shows that online engagement platforms can enhance transparency, improve accountability, and strengthen participation. However, effectiveness is limited by structural inequalities, institutional weakness, and socio-economic barriers. Thank you. That will be all from my side. Any questions?
Yeah, thank you. Now, the question is like you have mentioned two participation, the online and the offline. So, what would be the offline participation?
The offline participation is where people from government walk around door to door, like walk around the communities, trying to engage them in person.
All right. And how did you test your work? How did you verify it?
We verified using the already published articles. So it is a literature review. So we reviewed already published literatures from 2016 to 2025.
All right. So presently it is a literature, and in future you are going to implement it. Am I right?
Yes.
All right. All the best for the work. Thank you.
Thank you.
Thank you, Roneva, for the presentation. Okay, so next we have Supriya Narad to present her paper, which is image processing and deep learning for potato leaf disease detection. Supriya ma'am, are you present in the session?
Yes, ma'am.
Yes, so you can start presenting.
Ma'am, I have shared presentation. Is it visible?
Yes, yes, yes. It is perfectly visible. You can begin.
Thank you, ma'am. Good evening from India's time. I am Miss Supriya. I am presenting my paper on image processing and deep learning for potato leaf disease detection. This is the outline of my presentation. So why I have choose this topic, as the cultivation of potatoes has almost spread worldwide. So it is the crop that has been taken by Indian farmers in nation, as well as it is taken in outside the countries also. However, it is not always easy growing potatoes. So if we discuss about potato growing, so it is not always easy because climatic factors are one of the cause for it. Then plant diseases, mainly early blight and late blight, find out some trouble for those farmers also. In the case of dependence on farming, such diseases cause considerable economic loss and illness in plants with reduced yield of potatoes. In this project, we have concentrated on the implementation of a system to automatically diagnose plant disease in potato leaves in a special type of machine learning known as deep learning. So in this project, I am using deep learning. This is the methodology of my work. First of all, I am doing data collection of the images related to the potato leaf. Then I am performing some image pre-processing operations on that. I'm using CNN architecture because this methodology is using AI tools. Then after that, we need some of the leaps for model training and model evaluation also. So for data collection, I have used these potato leaves which are healthy as shown in figure. Sometimes they are early blight and sometimes they are late blight also. So the classes are healthy leaves, early blight, infected leaves, and late blight infected leaves. And in total, I am using 450 images, whatever are available to train and test the model. I have divided the number of images for training and testing purpose on a ratio of 80 is to 10 is to 10. The dataset comprised various images from light conditions and orientations of the leaves, which would subsequently help in the better generalization of the model. Then for image pre-processing, it is one of the most important steps in preparing images to be fed into a neural network for training. The pre-processing followed included resizing the images. For example, all images are resized into 500 by 500 pixels, so it will be the standard size that I am using here. Then for color space conversion, these images by default are BGR format that is used in the OpenCV library also. So converting them to RGB first. Then we have to manage the HSV parameters also. Then for image augmentation, several augmentation techniques were used. For example, data and lesson overfitting, rotation. Sometimes we have to do the horizontal or vertical flip operation, zoom in, zoom out operation, or we have to adjust the brightness also. Then in terms of methodology, I'm using here the CNN architecture. The CNN architecture is shown in the figure. It has some convolutional layers, many layers with ReLU activation engine. This is a type of activation engine used in CNN. And it will detect the patterns like edges, textures, or color variations. Then in pooling layers, there is a max pooling layer. It reduces the spatial dimensions because there can be some of the features related to spatial dimension also. They can be removed efficiently. Then dropout layer is there. This dropout layer randomly deactivate neurons during training to prevent the overfitting. Then there can be fully connected layers. These layers interpret the features collected to make the final classification. And finally, there is an output layer. This output layer will provide the output in terms of healthy early blight and late blight leads. Then I'm using the same data for model training purpose. So CNN model, it is compiled and trained using some of the configuration like optimizer I'm using here is ADA. Loss function is there, which has critical cross entropy. Metrics are accuracy and loss. Epoch is used there. For example, 20 to 50 epoch are used for training. Batch size is 32 for efficient training. In training and evaluation, 80% training data, as I have told you, and 20% for splitting can be used. Then this is about model evaluation. So accuracy of this model is achieved around 97.2% on the test set. Confusion matrix is used, and then precision recall, F1 score. These values are also calculated. So this is the output of that confusion matrix. For class healthy, precision is 0.98, recall is 0.97, F1 score is 0.975. For class early blight, the precision is 0.96, recall is 0.97, and F1 score is 0.965. Late blight, precision is 0.97, recall is 0.97, F1 score is also 0.97, and average I got it is 0.97. So overall accuracy, I can say 97.2 it is achieved. So finally, I'm concluding. So here in this research, I have used deep learning as a methodology. Then this system implements a convolutional neural network for identifying whether a leaf is healthy or it has been affected by early blight or late blight. And the accuracy achieved by the model stands at a high of 97.2%, thus enabling it to deliver trustworthy predictions. So these are the references that I have used. Thank you.
All right. Now, coming to the main challenge which comes here is visual similarity. So, how did you take care of that early blight rings of the potato?
Yes, ma'am. Sure.
So, could you tell me that how did you take care of that visual similarity in your work?
Yes, ma'am. So sometimes the leaves which are in classes early blight or late blight, there can be a similarity, but the based upon the standard data set that we are having, we have to find out the similarity and dissimilarity in between those leaves, ma'am, because whatever leaves we are taking, that may not be similar in classification also. So for similarity and classification, we should take care of the leaves in the learning phase itself.
Okay, did you notice any environmental changes? Like if the environment changes, there will be a change in the leaf.
Yes, ma'am. Sometimes
So,
there can be changes in the environment due to suppose rainy days are there or the days are sunny days. So there can be again the differences in the leaves. So the data set which is collected together belongs to a complete year, not in particular month, but complete year data set is managed for the healthy and blight leaves.
so does your model supports for the environmental changes?
Yes, ma'am.
All right. All right. Thank you.
Thank you, ma'am.
Okay, thank you, Supriya ma'am, for the presentation. You can stop sharing the screen. Okay, so our next presenter for today is Khadija Osmani Kosi to present her paper titled as Multimodal Artificial Intelligence for Cardiovascular Risk Stratification and Diagnosis in Athletes, a systematic review. So, are you present in the session, Khadija? Or
Okay.
any? Yes, you are there. So, you can start.
You see my presentation, please?
Yes, it is visible.
Thank you. Good evening, everyone. Thank you for this opportunity. I am Khadija Osman Kosi, a PhD student at Jakarta Job University. Today, I will present our systematic review, multimodal artificial intelligence for cardiovascular risk stratification and diagnosis in athletes. Let me begin with the clinical problem. This presentation is organized into 6 sections. The clinical background, objectives, and methodology, key finding, limitation, future direction, and conclusion. Let us begin with the clinical background. Sudden cardiac delay in athlete is rare, but among a major population has cancer, affecting approximately 1 in 14,000 to 18,000 athletes yearly. Distinction normal athletes heart adaptation for cardiovascular risks. This reason remains challenging kernel screening tool. Have important limitations. ECG has a 10 to 20 false positive rate, particularly in Black and Afro-Caribbeans. Echocardiography is operator dependent and cardiac MRE is expensive. Therefore, artificial intelligence is currently being expanded to improve cardiovascular screening and diagnosis. Artificial intelligence can detect the pattern in medical data, improving early diagnosis and cardiovascular risk stratification. However, most studies rely on a single modality, mainly ECG. With limited external validation and explainability, these gaps motivate our systematic review. Our review had 4 objectives: to evaluate AI diagnosis performance, identified the most effective AI model, and high barrier to clinical adaptation also, and propose recommendation for future multimodal and explainable AI systems. We followed the PRISMA 2020 guidelines. We conducted this systematic review according to the PRISMA 2020 guidelines, which ensured a transparent and reproducible skilled selection process. Our literature covered 5 major scientific databases. We showed PubMed, IEEE Explorer, SoundDirect, Web of Science, and Scopus. We initially identified 865 publications. After removing 124 duplicate records, 741 articles removed for screening. Abstract title, abstract, and full text screening. Many studies were excluded because they did not meet our eligibility criteria. Finally, 45 high-quality studies were included in our systematic review. This study founded the basis of our analysis. Next, I will briefly explain the eligibility criteria. We included a study using artificial intelligence or machine learning or deep learning for cardiovascular assumption in athletes. The selected study had to use ECG scanning, cardiac imaging, or clinical biomarkers. We excluded studies involving no athletes, a study without paper validation, and conference abstracts without full text paper. After selecting these studies, we analyzed it and compared their performance. This table summarizes the main AI model reported in the literature. One of our key findings is that multimodal AI consistently achieve better performance than unimodal approaches. For example, the multimodal transformer proposed by you achieved an IUC of 96%, where unimodal model generally represented IUC between 85 and 95%. The results highlight the clinical value of combining ECG, cardiac imaging, and another clinical information. However, our review also revolted several important limitations. Although multimodal AI shows excellent performance, it is still rarely used. About 75% of published studies rely on ECG alone, and only 8% combine 3 or more modalities such as ECG, imaging, and laboratory biomarkers. We also observed an important geographical imbalance. More than 75% of available datasets come from North America and Europe, while Africa and South America together accounts for less than 2%. This lack of diversity might limit the generalizability and feasibility of AI model approach. Another important issue concerns external validation. Many AI models achieve excellent results on their original dataset. However, when they are tested on independent hospital or different population, their performance often decreases. Across several studies, the IUC dropped by 5 to 10% during the external validation. More favor than 5% of published studies evaluate their model reproducibility and real clinical practice. This finding highlights the need for more robust multi-center validation before vaccine. Clinical implementation. This observation leads us to main challenge identified in our review. Our review identified 3 major barriers. The first, data heterogeneity. The second is representation based, and the third is explainability. In fact, fewer than 10% of a study including explainable AI methods such as SHAP, GAMT-CAM, or LIM, without understanding how those models source their decision. Clinicians may hesitate to trust and adapt them. So, how can fit research over these challenges? Fit research Future research should focus on developing multimodal AI systems that combine ECG, cardiac imaging, and clinical information. We also recommended building larger and international multi-center data sets with better representation of African population. Finally, explainable AI should be systematically integrated into future clinical decision support system to improve transparency and clinician confiance. This brings me to the conclusion of my presentation. In conclusion, AI has great potential to improve cardiovascular screening in athletes with multimodal approach of performing multimodal model. However, larger multimodal dataset with external validation, greater population diversity, and improved explainability are should needed before one clinical implementation. I sincerely thank my supervisor, co-author, collaborator, and institution for this report. Thank you to the organization of WorldS4 2026 and to all of you for your attention. I will be happy to answer your question. Thank you.
Yeah, thank you. May I know how did you, have you implemented or is it a review paper?
Please repeat again.
Have you done any practical implementation or is it a review paper? Is it a literature paper Sorry, say it again.
This people is strictly review people.
Okay, it's a review paper. All right. Then no questions from my side. Thank you.
Thank you.
Okay, thank you for the presentation.
Yeah, Ashika, we have how many more presenters now?
2 presenters left, ma'am.
All right.
No, actually, there's yes.
Sorry?
There's 1 presenter left.
Okay, then we'll complete that, then I'll go. Okay.
Yes, sure.
Okay.
So next we have Oluwaranti Omovani to present her paper titled as Variable Sensor Technologies for Ergonomic Risk Monitoring Among Construction Workers, a structured narrative review of implementation, accuracy, and occupational health outcomes. Oluwaranti, are you ready?
Yes, I'm ready.
Yes, you can start with the presentation.
Yeah, I'll go ahead now and share my
Yes.
slide.
You have 10 minutes.
Yep. Can you see my slide? Am I?
Yes, it is visible.
Yeah, okay. So just give me a moment. So this morning, imagine a construction worker completing an 8-hour shift every single day. And throughout the day, they repeatedly bend, they kneel, twist, and walk overhead. Yet, traditional ergonomic risk assessment only capture a small portion of these activities. This raises an important question. Are we truly measuring workers' ergonomic risk, or we are simply taking a snapshot? This is where wearable sensor technology offer a promising solution to manage this risk and support injury prevention. My name is Oluwaranti, and today this review was conducted to address the gap that although wearable sensor technology offer a promising solution to reduce ergonomic risks, but there is a problem of implementation challenges, most especially in the real-life construction settings. So in today's roadmap for the presentation, I'll start with the background. That's why wearable sensor technology is important, followed by the methodology used in this review. I'll go ahead and present the key findings, the prevention, implication, practical implication, and the future directions for the research. So why should we care? Construction workers face one of the highest economic risk level. And this is as a result of the physically demanding tasks that involve heavy lifting, twisting, body movement, body vibration, heavy manual handling, which created a lot of burden on the workers, leading to musculoskeletal disorder. And a pool of studies reported that 59% of workers experience work-related musculoskeletal disorder. And the traditional risk tools like RIBA and RIBA, that's Rapid Entire Body Assessment, and RULA, Rapid Upper Limbs Assessment, they are subjective in the sense that two ergonomics scores may vary between workers. And aside that, the traditional assessment tools only capture for a moment. It does not go out throughout the shift of the entire day to be able to monitor the worker. So it's only a momentary assessment. And this creates an opportunity for wearable sensor technology. So moving on to the next slide of my research questions. For this review, the research questions, 3 research questions was provided. And then this is to aim us to provide a proper understanding of wearable sensor used in monitoring economics for construction. So the first research questions, it's examine what type of wearable sensors that are currently being used in construction industry. And then the second research questions evaluate how accurately these sensors can detect ergonomics risk factor. And the last research questions explored the barriers to implementing work-related, to implementing wearable sensor technologies, and as well as their health impact outcome on the workers. So to answer the research question, a structured narrative review was conducted across 5 databases, that's PUMA, Corpus, and the rest, between 2017 and 2024. So with the search, this was screened systematically to ensure that only peer-reviewed empirical studies that investigated wearable sensor technology in the construction industry were used for this paper, for this review. And then once the identified studies were selected, a review was done to make sure to evaluate and identify the various type of wearable sensors, the current state of it, and the implementation challenges of it, and the future research that guided the review. So moving on to the next slide, which is wearable sensor technologies. So to answer one of the first research questions, which examine the type of various wearable sensors that are currently being used, the review identified the 6 categories, which were inertia measurement units that monitor body movement, orientation, posture, wearable insole pressure, it measures the foot pressure, awkward postures in workers. Moving on to surface electromyography. This is particularly useful, most especially when performing over-exertion as a result of manual handling, heavy manual handling from workers. So we also have the heart rate that monitors the physical stress on the body, going to the cardiovascular strain of the workers, and then the smartphone sensors that can be wrapped around the hand that monitor the body movement, the shoulder and trunk posture as well. So one of the key findings of this research was that under control studies, based on the review, wearable sensor technologies reported highest accuracy from that's about 85 to 99.01%. That's one of the highest accuracy we've gotten from this very review. But however, due to the dynamic nature of construction, in real life construction setting, as a result of factors that involve dust, vibration, motion artifacts, and a lot of other factors, this does not really show high accuracy, and only under control studies based on the review that has been conducted. So it does not really categorize the studies under the real construction site where the actual thing is actually happening on the site for us to be able to get the higher accuracy. So moving on to the challenges to a real-world implementation of wearable sensor technology. Even though wearable sensor technology offer promising solution, implementation present practical challenges such as environmental conditions like dust, heat, or being the cold weather or winter. So all this needs to be taken into consideration when validating this very wearable sensor. The motion artifact, the privacy and security of data, even workers' adoption also play a role in challenges of this implementation as well. To battery and data usage, physical comfort, and multi-employer structure. This is most especially construction setting. We could have like more than one contractor on a side. It could be like 10 contractors. Managing this between them always also have to be some of the challenges with the multi-employer structure nature of construction setting. So the next slide is from monitoring to injury prevention.
Just a quick
Wearable
reminder,
sensors.
you will have to wrap up in next few seconds because already it's
Yes.
10 minutes. Yeah.
Thank you. I'm almost done. Thank you. So wearable sensor do not prevent injury on its own. People and organization do. So wearable sensor can provide some sort of information for us. We analyze the data, but organization need to come in to ensure works of workers are modified to engineering control, giving adequate training, and overall this improve workers' health by reducing the work-related economic risk and then prevent injury, overall improve the workers' health. So these are my practical implications. There's three group of people needs to benefit from this. The workers, early risk with the wearable technology, there's early risk reduction for them. And the employer through the data driven using from wearable sensors that are collected, it can be integrated to be more proactive in supporting the economics program for them. But for researchers, they still need to ensure that these are really practicable in the real life, in the real construction setting. And also to develop AI-driven, risk-driven to be able to predict more data information. So, and this is for the future research that wearable sensor offer promising solution. More research is needed in the practical real world of construction, more data, more real world validation to be able to ensure it's actually measured, it's actually reduced work-related disorder. And then I'll conclude with my conclusion. It's for this review is that wearable sensor do offer promising solution for us, but real life implementation offers some challenges, and in the real sense, there is evidence that more validation is needed from researchers to be able to ensure these are validated and ensure driving data as well. So, thank you.
Yeah, thank you. No questions from my side.
Thank you. I'm open to any question.
Yes, thank you so much, Olu Varanti, for your presentation. So I think we are good to conclude as this was the last session for today. So there are a few announcements to make. 1 second. Yes, so on behalf of the Global Knowledge Research Foundation, GR Scholastic LLP, and the entire WorldS4 2026 organizing team, I sincerely thank all our authors for their excellent presentations, valuable research contributions, and active participation. A big thank you to all our attendees for making this session interactive and engaging. And this is the 10th edition of WorldS4. We deeply appreciate your continued support over the years, and we look forward you all to welcoming you again in the 11th edition in 2027 as well. So a few announcements: all presenters will be receiving their digital certificates through email within 2 working days, and the conference publication is expected to go live within 7 to 8 months. So we kindly request your cooperation with the World S4 2026 team. I would also like to express our sincere gratitude to our respected session chair, Dr. Preeti Parvekar, ma'am. Thank you so much for joining the session. And this is a small token of appreciation on behalf of Global Knowledge Resource Foundation and the whole conference team. Before concluding, I would like everyone to please switch on their camera for a few seconds so that I can click a quick snapshot of the conference. One second. Let me. Yes, thank you all once again. Stay safe and have a wonderful day ahead, everyone. Thank
Thank you.
you for joining.
Thank you.